Hello everyone. In this video, I continue talking about forecasting. In the previous video, we started talking about forecasting methods, and we gave several examples for subjective forecasting methods and mentioned that we will mostly concentrate on objective forecasting methods. And also in the previous video, we talked about causal models, which belongs to objective forecasting methods, and started to talk about time series methods. We can classify time series methods into two groups as methods for forecasting stationary series and trend-based methods. In this video, I will talk about methods for forecasting stationary series, and I will introduce two important, very popular and practical forecasting methods. These are moving averages and exponential smoothing. Let's start with the method moving averages. This is a simple but very popular and practical forecasting method. We have a parameter n. We call this as order n, and we have to determine this n before applying our method. And in this method, what we do is to simply take the arithmetic average of the most recent n observations. Here is the formulation, as you can see. We take the most recent n observations, sum them up and divide with n. We take the average and we obtain the forecast for the next period. Here we will use the notation MA in parentheses n for n period moving averages. Here is an example for moving averages. We have quarterly data for the failures of certain aircraft engines at a local military base during the last 2 years. Here are the observations. We have 8 observations for these last 2 years. And both 3-quarter and 6-quarter moving averages are used to forecast the number of engine failures. We choose n as 3 and 6 to forecast the number of engine failures. And it is asking to determine the one step ahead forecast for periods 4 through 8 using 3 period moving averages, and the one step ahead forecast for periods 7 and 8 using 6 period moving averages. And let's solve this example. Here in this table, you see the data for these 8 quarters. And for periods 4 through 8, we will calculate the forecast using moving averages order 3. What we do is that, for example, for period 4, we take the most recent 3 observations. The data belonging to quarter 1, 2, and 3, and we take the average of this data and use as our forecast. And for period 5, now again we will use the most recent 3 observations. So in this case, we disregard the data of the first quarter and only take the data belonging to quarters 2, 3, and 4 and take the average of these 3 observations and obtain our forecast. Here in this column, the errors are given. We obtain the error by the difference of our forecast and the real observation. And we go on like this. And for periods 7 and 8, it is asking to calculate the forecast by using the method moving averages order 6. In this case, what we do is to use the most recent 6 observations. For period 7, here we take these 6 observations and take the average. And for period 8, again we take the most recent 6 observations and take the average. Here in the last column, the errors are given. One of the disadvantages of the method moving averages is that when we have a new observation, we have to recompute the average of the last n observations each time. In fact, what we have to do is to take the new observation and disregard the n periods old observation. So, in fact, when we rearrange the formulation in this way, as you can see, if we take the difference of the new observation and the n period old observation and divide with n and sum with our latest forecast, in fact, we obtain the new forecast. So instead of taking the average of the last n observations each time, we can only use the new observation and the n periods old observation to compute our new forecast. Now I would like to give another example for the method moving average. In this example, we have a demand data, but this data has a special property. The numbers are increasing regularly. As you can see, in each period, demand increases in 2 units. Now, in fact, we wonder what would happen when we apply the method moving average to such a data, in which there is a defined trend. We will apply moving averages order 3 for periods 4 through 12, and we will apply the method moving average order 6 for the periods 7 through 12. Here this graph shows the real data and also our forecasts. Here is the forecast we obtained when we applied moving averages order 3, and this third line shows the forecast when we applied the method moving averages order 6. As you can see from the graph, in fact, our forecast is also increasing regularly, just like the real data. But as you can see, in each time we are underestimating. So we can say that this method lags behind the trend. So we can conclude that if there is such a trend in the data, moving averages method isn't suitable for such data. After talking about the method moving averages, now I will start talking about the method exponential smoothing. In this method, the current forecast is calculated by the weighted average of the last forecast and the current observation. That is, new forecast is equal to alpha multiplied with the current observation plus 1 minus alpha multiplied with the last forecast. In symbols, we can show in this way. Here, alpha is the weight that we assign for the current observation, and alpha is a number between 0 and 1. In fact, this is a parameter that we have to determine before applying this methodology. It is just like the parameter n in the method moving averages. We have to determine the number of the last observations to use in moving averages method. Just like that, we have to determine the weight to assign for the current observation in exponential smoothing. And as you would guess, when we increase alpha, it means that in fact we give more importance to our current observation. Whereas if we decrease alpha, it means that we give more importance to past data. And it is just like in moving averages. If we increase n, if we take more observations, it means that we give more importance to past data. But if we decrease n, it means that we take more recent data and we give more importance to the recent data. Here is the formulation for the forecast, and when we rearrange this formulation, we can obtain this formulation, And as you can see, ft minus 1 minus dt minus 1 is equal to the error we have done in our previous forecast. So in fact we can rearrange this formulation in this way. Our new forecast is equal to our previous forecast minus alpha multiplied with the error of the previous forecast. Here, from the formulation, you can see that if our error is positive in our previous forecast, I mean if we overestimate in that forecast, then in this forecast the formulation will decrease the forecast. But vice versa, if we underestimate in the previous forecast, I mean if the error is negative, in that case with this formulation we will increase our forecast value. The first line is the original formulation for our method exponential smoothing, and from that formulation, in fact, we can write the forecast for the period t minus 1 in this way. And if we insert this second formulation into the first formulation, here we obtain this third line. Again, we can write the formulation of ft minus 2, and when we insert this formulation in this formulation and if we continue in that way, in the end we will obtain such a formulation. In this formulation, as you can see, we are assigning weights for each of the observations, and the weight is alpha multiplied with 1 minus alpha to the power e. E is the age of the observation, and as you would guess, if the age of the observation increases, since it is to the power, then this number gets smaller. In fact, what we conclude that in this exponential smoothing methodology, we assign weights to each of the observation, but the weights are decreasing as the age of the observation increases. And when we sum up all of the ages, when we sum up all the weights, here, as you can see, we see that the sum of the weights is equal to 1. And now I will show the weights on a graph. Here, if alpha is 0.1, as you can see, the weight that we give to the most recent observation is 0.1. Then for the weight decreases exponentially for the rest of the data. For that reason, in fact, we call this method as exponential smoothing. In this method, we use all the observations, we assign weights to all of them, but the weights are decreasing exponentially, as you can see from the graph. And as I mentioned before, when we increase the alpha value, it means that we give more weight to our recent observations. But if we decrease the alpha value, we also give importance to the past observations. And when the alpha value is high, then in fact this forecast will react more quickly to the changes in the demand, but we will have more variance in our forecast. But when the alpha value is small, it means that we will have a more stable forecast. I will show this in an example. Here is an example for exponential smoothing method. In fact, this is the same example we use for the method moving averages. Here is the data of the number of failures over a 2-year period. And now we take alpha value as 0.1 and we will use exponential smoothing method to be able to forecast the number of failures in each of the quarters. In this method, we use our last observation and also last forecast. When we are at quarter 1, we don't have any last forecast. For that reason, we assume that our last forecast is the same as our last observation. I mean, it is 200 for this example. Okay, we are at quarter 1 and we want to forecast the number of failures for quarter 2. Here is the formulation. We multiply the last observation, which is 200, with alpha value plus 1 minus alpha value multiplied with the last forecast, and we obtain the value 200 as the number of failures for the next quarter as our forecast. And let's check the next equation. Now we are at quarter 2 and we want to forecast the number of failures for the quarter 3. Here we multiply alpha value with the last observation, which is 250, plus 1 minus alpha value multiplied with the last forecast value, which is 200, and we obtain 205. And we do this for each of the quarters. Now let's see our forecast values on the graph. Here on this graph, this bold line shows the real observations, and the second line shows the forecast values when we take the alpha value as 0.4, and this third line shows the forecast values when we take the alpha value as 0.1. As you can see from the graph, when alpha value is higher, for example 0.4, the values of the forecast can more easily react to the changes. But when alpha value is less, as 0.1, we obtain a more stable forecast, as you can see on the graph. Now let's compare the forecast values that we obtained from the methods moving averages and exponential smoothing. You know, we applied both of the methods to the same example. And now I take the n value 3 for moving averages method, and I take the alpha value as 0.1 for the exponential smoothing method. And this table shows the mean absolute deviation and mean square error that I obtained by using both of the methods. As you can see, both of the measures are higher in the moving averages method. So, in fact, does it mean that the values that we obtained by exponential smoothing method is better than the values that we obtained moving averages method? No, because the parameter settings are important. We chose n value as 3 and alpha value as 0.1. But are these settings consistent? We have to firstly check this. When I observe the forecast values for the moving averages method, I see that there is more variability than the values that we obtained from exponential smoothing method. So this means that in fact these parameter settings are not consistent. To be able to make the parameter settings consistent, we can equate the average age of the data used in making the forecast. In moving averages method, we use n observations, and the weight assigned to each of the observation is 1 over n. To be able to calculate the average age, we can sum up all the ages and multiply with the weight assigned to these ages, and obtain that for the moving averages, the average age of the data is n plus 1 over 2. And for the exponential smoothing method, We know that the weight assigned to each of the observation is alpha multiplied with 1 minus alpha to the power e minus 1. Again, if we multiply this weight with the age of the observation and sum them over, then we can obtain the average age. And for the exponential smoothing method, we obtain the average age as 1 over alpha. And when we equate the average age of the data for exponential smoothing method and average age of the data for the moving averages method, in fact, we can make the parameter settings consistent. Here, according to this equality, if we take the alpha value as 0.1, then we have to choose n value as 19. Or if we are choosing n value as 3, then we have to choose alpha value as 0.5. In that case, we can make a comparison between both of the methodologies. But this doesn't mean that when we set the parameter settings in this way, we will obtain the same forecast values. This means that only we know that when these parameter settings are consistent, both of the methods will have exactly the same distribution of forecast errors. And now let's talk about multiple step ahead forecast. Up to now, we only talk about one step ahead forecast. But however, there may be cases when we are interested in making a forecast for more than one step ahead. For example, think about that there is a retailer and we are in month June, and the retailer wants to make plans for Christmas, and he wants to make a forecast for the month December. But in June, the forecast that he will make for July will be same as the forecast he will make for December if he uses the methods moving averages and exponential smoothing, because the underlying models assumed for both of the models are stationary. I mean, it is not changing in time. For that reason, even we are making multiple step ahead forecasts, in fact, we will obtain the same forecast with one step ahead forecast. So, if we want to make multiple step ahead forecasts, two of the methodologies are not suitable for this. Now I will compare both of the methods that we discussed. Firstly, I want to start with the similarities. Firstly, both of the methods are obtained with the assumption that the underlying demand process is stationary. I mean, if there is a trend in the data, then both of the methods are not suitable for that data. They will lag behind a trend if one exists. And in both of the methods, there is a single parameter that we have to specify. For moving averages, we have to specify the value n, which is the number of periods in the moving average. And for exponential smoothing method, we have to specify the value of the alpha, which is the smoothing constant. As I mentioned before, if we decrease the value of n, it means that we give more importance to recent observations. If we increase the value of n, it means that we also give importance to the past data. And in the exponential smoothing method, if we increase the value of alpha, we give more importance to the recent data, whereas if we decrease it, we also give importance to the past data. And to be able to compare both of the methods, we have to equate the age of the data, and by the equality alpha is equal to 2 over n plus 1. Both of the methods have the same distribution of forecast error. This means that they should have roughly the same level of accuracy, but it doesn't mean that they will give the same forecasts. And now differences. The exponential smoothing forecast is a weighted average of all past data points, whereas the moving average forecast is a weighted average of only the last n periods of data. In order to use moving averages, one must save all n past data points. In order to use exponential smoothing, one need only save the last forecast. This is the most significant advantage of the exponential smoothing method and one reason for its popularity in practice. And in this video, that is all that I want to talk about. And we will continue talking about trend-based forecasting methods in our next video. See you.